Hey everybody, this video is about the primary functionality of the LPC1768 microcontroller that we are using in our PCB. Now, first to explain you what the microcontroller is primarily doing. It has, the main thing that it's doing is that it's charging the supercapacitors at an optimized rate. What do I mean by optimized? By optimized I mean that it needs to take care of two things. First, that it doesn't allow a lot of current to pass through the PCB, the buck and the boost circuits. If it does so, it can damage the circuits. And secondly, it has to ensure that it charges the supercapacitors at a very good pace. So that's in this video we're going to demonstrate that functionality to you. So we have the hardware setup here. As you can see, it's already explained in the hardware description. But we have additionally some multimeters here. First we have this yellow multimeter which indicates the amount of voltage that is there currently in these supercaps. So they're charged up to 7 volts, and as already explained that they can have a total voltage of 21 volts. Then we have this red multimeter here. It's reading 0 right now because we don't have any input supply. It indicates the current that's coming from the input source. In this case, it is the power box here. And then we have this gray multimeter here, which is also reading approximately 0. And this indicates the amount of charge that's flowing to the supercapacitors. If it has a negative value, it means the current is actually flowing from the supercapacitors. If it has a positive value, that means the charge is flowing to the supercapacitors. And now we have the gray multimeter here, which reads approximately 0, but it's not exactly 0. You can see that there is a small value over here, 0.06, and that's because the supercapacitors are powering a few things in this PCB, including the LEDs, and then the buck and the boost circuits. So these things are being powered by the supercaps, and hence you can see that's 0.06 current is actually flowing from the supercaps. Okay, so now we run our test here, and before starting the test, I would like to tell you that we aim to maintain the amount of current flowing through the buck and the boost circuit at around a particular threshold. And why we do that, I've already explained that we don't want to damage our circuit, and we want the supercapacitors to charge at a good pace. So the threshold that we will use in our test case is 1 amperes. And so you will be able to see in the gray multimeter here that we want to maintain the current around 1 amperes. That is, the current that is flowing to the supercaps should be around 1 amperes. Also, we have two cases here. The first case, where from the input we have a voltage higher than that which is there in the supercaps, and the second case, we would have a lower voltage in the input. When we have a higher voltage in the input, we want to use the buck circuit, and when we have a lower voltage in the power input than the voltage that we have in our supercaps, we want to use our boost circuit. So initially we will turn this on, but we'll keep a voltage over here higher than that which is there in the supercaps so that our buck circuit runs. So first I'll turn this on, and I'll keep a voltage of around, actually it's enough, it's 11 volts here, and we have 7 volts in our supercaps. So we know that the buck circuit is going to work. Now here I can show you, I've logged into the microcontroller, to the microcontroller serial interface. The command that we are using here to start the test is test start, and I press enter, and now the test has started. It starts from a duty cycle of 80%, and as we can see here that now the current is being maintained at around 1 amperes. What we do is that if the current decreases, we increase the duty cycle, and if the current increases, we decrease the duty cycle. And that's how the microcontroller intelligently maintains the current at around 1 ampere. So as you can see, it's approximately averaging at around 1 amperes. Now what we'll do, and we can also see that the supercapacitors are charging at a slow pace. And now we'll increase the voltage in the input. And we see that it's still being maintained at 1 amperes, although we have a higher input now. Now, in order to switch to the boost circuit to demonstrate you how that works, I will decrease the input voltage to a value less than the voltage in the supercapacitors. And as I decrease it, you can still see that the current is adjusting. The duty cycle right now that I can see on my computer screen is approximately 94%. I decrease further. And now it has already switched. This is an LED indicating that the buck circuit is working now. And we can see that the boost circuit is working now, and we can see that the current is somewhere around 0.5 amperes. So if I decrease it further, so as I decrease it, now the voltage is at around, as you can see, around 5 volts. And the voltage in the supercaps is 7.36. But you can clearly see that although the voltage that we have in input is less than the voltage that we have in supercaps, there is still current flowing into the supercaps, which means the boost circuit is boosting the voltage up, and we have some current going into the boost circuit, into the supercaps. As you can see over here, this is the voltage, this is the amount of current that is flowing from the input, and this is much higher. That's because we have a lower voltage in the input, and so we have a higher current in the input, but we have a higher voltage in the output, and so we have a lower current in the output. And that is how the boost circuit is operating. So now we're going to show you how our PCB and the rest of the hardware setup works with the load and how it behaves when there is a power failure. Now the voltage that we have in the power box is higher. It's around 10 volts, and the voltage that we have in our supercaps is around 7. So we can see that the buck circuit is operating here, and the current that we see over here is around 0.1 amperes. So the supercaps are charging with a current of 0.1 amperes. The load is not connected yet, and this is the load, which is a Bifrost router, and I have a power cable here which comes from the supercaps, and I will now connect the power cable to the supercapacitor, to the Bifrost router. And you must notice the change on this multimeter, and you can see there was a sudden change from around 0.9 amperes to 0.5 amperes. So we can see that the router is using approximately 0.4 or 0.5 amperes of current, but we can still notice that we have a positive value here, which means that the supercapacitors are still charging. So now we have the supercapacitors charging as well as the load powered. And you can also see on the multimeter that the voltage is going to increase slowly because the supercapacitors are charging. You can see it moved from 7.70 to 7.7, and this is the total amount of current that we have from the input. So now I'm going to demonstrate what's going to happen when we switch off the power supply. For instance, when there is night time, we won't be having the solar panel at the input. So if I switch it off, now you must notice the change on the multimeter again. I've switched off now, and you see that now we have a negative value here. What does this indicate? This indicates that we have 0.65 amperes of current flowing from the supercaps. And where is it flowing? It's flowing to the load. It's actually powering the load. So we can see that when there was a power failure, the supercapacitors still support the load, although we don't have any current or any power flowing from the input. And you can also see in the multimeter here that the charge has started decreasing. We had it on somewhere around 7.71, and you can see that it has reduced to 7.66 because the load is now extracting power from the supercapacitors.